Hello, this is lecture 4 in my sequence of lectures on robust statistics. In this lecture, we will begin to develop the machinery that we need to create efficient algorithms for robust mean estimation in high dimensions that don't lose these dimension-dependent error factors. The fundamental concept that will underlie all these things is a concept that I like to call spectral signatures, which was first used in the paper by Brandon Tran, myself, and Aleksander Madry, in the context of a much more complicated problem actually, but the fundamental geometric fact is the same. And what it says is that corruptions to lower order moments of a distribution caused by a small number of outliers necessarily results in a large perturbation to the spectrum of higher order moments of the distribution. So that's a little bit abstract, but let me just try to make this more concrete with a picture. So consider the setting, which is supposed to represent high dimensional data. Here the black points are nice ID samples from a distribution, and the red points are outliers, trying to mess up the mean of the distribution. So you can see the true mean of the distribution is supposed to be something like near the origin. But because of the outliers, the empirical mean of my data set actually lies somewhere over here. So there's a large shift caused by these small fraction of outliers. Let's consider what this must do to the covariance of the data. So the true covariance is supposed to be nice and spherical, sort of like this. But because there is all this action along this direction, caused by the outliers, the empirical covariance will actually be stretched in this direction because there's going to be just much more happening in this direction than there should be, and so the empirical covariance will actually look something like this. So there will be a large kind of bulge in this direction, and this is essentially a large eigenvector of the second moment, and this is what I call a spectral signature. In other words, the fact that there was this deviation in the mean caused by this outliers, the fact that this was a large deviation, induced a large eigenvector in this direction. And this is a spectral signature, which is very useful because it gives us an efficiently checkable certificate that the mean has been corrupted, because I certainly can't verify this property easily. I certainly can't verify that the mean has been shifted. That's the whole problem after all. But I can certainly compute the top eigenvector of my empirical covariance matrix. And if that's too large, then I know something's wrong. Alternatively, if that's small, if that's sufficiently small, then actually I know that things are fine, that I don't need to worry about like anything. I can just output the empirical mean. It hasn't been corrupted. So let's make this concrete. In this lecture, we'll do so in the context of bounded second moments. Later on, we'll also do so for Gaussians. But in this lecture, we're just going to prove the following theorem. Actually, we're going to prove something slightly more general. But nonetheless, theorem. Let epsilon be less than 1. Let S be a set of points of the form that hopefully by now we're familiar with. So S is equal to S sub good union S sub bad set minus S sub removed, where S sub removed is a set of points I remove from S sub good, and S sub bad is a set of points I add, and neither of these points have large cardinality, so their cardinalities are both upper bounded by most epsilon n. Then let mu sub good be the empirical mean of the good points. You should think of this as the true mean I'm going to try to recover. And I will make the following assumption. I will assume that the empirical covariance of the set of good points, which is simply this matrix, has no large eigenvalues. So, in other words, it is spectrally dominated by C times identity. So all its eigenvalues are most C. Then in this setting, we have the following conclusion, which is that if I let mu hat be the empirical mean of my corrupted set of points, and sigma hat I will let to be the empirical covariance of my corrupted set of points, then we have the following, that the LT norm between mu sub good minus the empirical mean can be upper bounded by 1 over 1 minus epsilon times the following quantity, square root 2c epsilon plus square root epsilon times the spectral norm of sigma hat, the empirical covariance. So this is exactly the sort of contrapositive to the statement that I was saying above. In particular, suppose that the spectral norm of sigma hat was upper bounded by, let's say, order 1. Well, then that means that the difference between the true mean and the empirical mean is upper bounded, at least when epsilon is relatively small, by order root epsilon, which, if you recall, in this setting is the best you can ever hope to do. So this says that if I want to check if the empirical mean has been corrupted, one valid certificate is to check if the spectral norm of the empirical covariance is not too large. And if it is not too large, then we know that we're done. We can just output the empirical mean. And let me just briefly recall So the spectral norm of sigma hat, well, this is by definition the supremum over all unit vectors, V, V transpose sigma hat V. And this is a slightly nice form that we're going to use later on, because sigma hat is an empirical covariance matrix. So I can rewrite this as sup over the same set of 1 over n times sum, let me just erase this, V transpose times sum of x minus mu hat, x minus mu hat transpose V. This sum is over S. And I can just bring the V's inside. And this just becomes sup over V with unit norm of 1 over n times sum x and S of x minus mu hat inner product V LT norm squared. So in other words, it's maximizing this degree 2 polynomial over the unit sphere. So this will be a useful fact later on. So we'll actually prove a slightly stronger version in this class. In particular, all of our algorithms will assign non-uniform weights to our points. Ideally, we will assign large weight to good points and 0 weight to bad points. But that means it will be important to have some version of the above theorem that also works when you have non-uniform measures over my points. So let's introduce the following important terminology, which we will use repeatedly through this next set of lectures. So let me index my set S as x1 through xn. And then let me define this quantity gamma sub S, which is a set of weights over 1 through n, which are non-negative and sum to at most 1. So in particular, if the sum of the weights was exactly 1, this would be the simplex, just the standard simplex, but it's more like a subsimplex, because I allow the set of weights to be summed to less than or equal to 1. Then, for any non-zero set of weights in gamma sub S, I can define this quantity mu of w, which is the empirical mean with respect to the set of weights. I define it to be as follows. I define it to be 1 over the L1 norm of w times the sum of wi xi. So the 1 over w L1 norm is simply a renormalization factor to make w actually a probability distribution. And I can also define the empirical covariance with respect to this w. So I can define sigma of w to be sum I and s of wi times x of I minus mu of w times x of I minus mu of w transpose. So if I was going to be super proper, I would also have a normalizing factor of 1 over L1 norm of w here, but it turns out it doesn't matter too much, so I would just neglect that here. Also, let me introduce the following terminology, which is that if w and w prime are two elements of this subsimplex, such that wi is less than equal to wi prime for all I, that is, w is totally dominated in every coordinate by w prime, then I'll just write w is less than equal to w prime. So let's consider the set of weights we're going to want to consider. It's going to be a subset of the points in the subsimplex, ideally a convex set because we like optimizing over that kind of set. Ideally, what we're going to want to do is our algorithm is hopefully going to place all our mass of our set of weights over the uniform distribution over the remaining good points, so over S sub good intersect S. Now, all we know about this set right now, before actually looking at the points, is that it has large size. It has size at least, or exactly, 1 minus epsilon times n. So in particular, the set of allowable weights should also contain the uniform distribution over all sets of that size, maybe up to some normalization factor. And this motivates the following definition, which is the following. So for all t, which are subsets of S, let w of t be the set of weights which are 1 over n if I is in t and 0 otherwise. So we want to contain all these weights for t which are size 1 minus epsilon n, and because we like things to be convex, we'll actually take the convex hull of the set of weights. So we want the convex hull, we want this set here. So let me just define script w sub n comma epsilon, which I'll sometimes just write or refer to as w, as this quantity. And if you think about it a little bit, it turns out it has a relatively nice form. So it is simply the set of weights in my subsimplex, such that w is dominated by the uniform distribution, so it's less than 1 over n in every coordinate. And moreover, the L1 norm between w of s the uniform distribution over S, and W is at most epsilon. Okay, so it turns out that these two, this is equivalent to the convex hull of the thing I wrote above, and this is not too hard to prove, so I will omit this proof. But then this set has two nice properties. So first of all, notice that the uniform weights are indeed in this set, simply because they very clearly satisfy these properties. And secondly, this set has very small width. So in particular, for all WW prime in this set script W, the L1 norm between W and W prime is at most 2 epsilon, just by triangle inequality with W of S. Okay. Now with this terminology, we can state the more general thing that we're going to prove. In particular, what we're going to prove is essentially a spectral signature theorem, but for sort of these soft subsets. So anything within any set of weights within this set script W. So in particular, lemma, let epsilon be as before, let S, which is S of good union S of bad, set minus S of bar, be as before, and mu sub good be the empirical mean of S of good. And assume again this condition star, that S of good has bounded covariance. Then for all W, which are in this set of reweightings in script W, we have the following, which is that the L2 norm difference between the true mean and the empirical mean of with the reweighting W is upper bounded by the same quantity as before. So notice this is strictly more general than the statement that I had before, because again the uniform set of weights over S is included in the set script W. So I can always just replace this with mu sub S, and then I recover the original theorem. So this is a strictly more general version of the previous theorem. So this is what we're going to prove in this lecture. We're only going to use essentially one non-trivial inequality. I use non-trivial slightly loosely here. We're just going to use a very basic version of Holder's inequality, which whose proof again I will omit because it's a very simple exercise. So the fact is the following: let A1 through AM and B1 through BM just be any real numbers, and let W be any element of the subsimplex. Then we have the following, which is really just a very basic version of Holder's inequality, which is that sum of Wi AI Bi quantity squared can be upper bounded by sum of Wi AI squared times sum of Wi Bi squared. So again, this is very easy to prove. I will omit this proof. However, I should actually note that it's kind of important. It will be important, at least later on, that this is essentially the only thing that we use in this proof. Because the fact that our proof only uses very simple proofs itself will mean that our proof will lift to this so-called sum of squares hierarchy. And this will be very important for some of the later algorithmic results. But for now, that's not super important. Just remember that this proof is only going to use some very basic algebraic inequalities. So let's prove this lemma. So let's first do some, let's get some of the notational stuff out of the way first. Let's adopt the convention that let me extend W, the set of weights, to not just S, but also the points in S of R in the trivial way. Let me just say Wi is equal to 0 for all xi in this set of points S removed, or S of R. And let me also just call delta this vector mu of W minus mu sub G. So this is the thing that we want to upper bound in L2 norm. So the first step in this proof is going to be a sequence of just equalities. So I wrote them out here because if I try to write them out, I'm going to mess them up. But this is just a sequence of equalities, not inequalities. So nothing is actually happening here. I'm just rewriting these quantities. So I'm going to rewrite this quantity, which is the L1 norm of W times the L2 norm of delta quantity squared, for some reason, and it'll become clear later on, hopefully. So what is this quantity? Well, let me just expand it out, and let me expand it out in a slightly weird way. So I'm just going to keep the L1 norm of W as is. I'm going to write this as delta inner product mu of W minus mu sub G. So I'm going to keep one delta as is, and I'm going to write one other copy of delta as this expanded form for some reason. Okay, so then let me just rewrite this expanded part. Let me expand it even further to be just, this is by definition, just 1 over the L1 norm of W times the sum from I equals 1 up to n of wi times xi minus mu sub good. Good. So now these wi's cancel, and I have this slightly nice form by pulling out the summation. So this is actually also equal to sum from I equals 1 up to n of wi times the inner product of delta with xi minus mu sub good. Okay, so this is all equalities. And now the next step will just be to even split this up into more equalities. So the sum from I equals 1 up to n, so this is a sum over s. I can split it up into the sum over the points in s good. So this is a slight abuse of notation, but I'm just going to write I in s good to mean that xi is in s of good. So this is a sum over the points in s of good of this quantity plus the sum of the points in s of bad of this quantity. So I will deal with these 2 points, or these 2 sums separately. So let me call the first one a sub good and the second one a sub bad. Okay, so now let me do some more rewriting of a sub good. Again, so far these are all going to be equalities. So still nothing is happening. That's very interesting. I'm just rewriting things. So what I'm going to do with a sub good, recall the only thing that we know about our set of good points is that if we take the uniform set of weights, we have some bounded covariance properties. So that means somehow I need to relate this to the uniform set of weights. So let me just add and subtract what happens if I take the uniform set of weights. So then I can write a sub good as simply the sum of the uniform set of weights of this inner product of delta with xi minus mu sub g plus the sum over the rest. So wi minus 1 over n times delta inner product xi minus mu sub g. And this is actually a little bit nice because if you think about it, this term is actually 0. And that's simply because what I'm doing is I'm taking the inner product of delta with the average of the x sub i's in s sub good minus mu sub good. But this second term is actually 0 over this set because the average of the x sub i's is mu sub good. So all I'm left with when I do this is simply the second term, which is sum from over I in s sub good of wi minus 1 over n times this inner product. And recall that I've defined wi to be 0 for all I in s sub removed. Okay, so that's the first part of the sum for now. Now let's deal with a little bit with the second part of the sum. So this is a sum of the same thing over the bad points. And what I'm going to do is I'm going to just add and subtract mu of w, so the empirical mean over the weights w. Okay, this is totally allowed. It's not entirely clear why we're doing this yet, but it's certainly allowed. And when I do so, what I get is the following. So here, I've added and subtracted mu of w. And in this term, I get this. And this term, notice that the sum actually doesn't depend on I anymore. And moreover, mu of w minus mu of good, this is delta. So this is delta. So I get inner product of delta with itself squared. And I get this times the sum of the weights of wi for I in s bad. So if you scroll back up, and you realize that I have a delta L2 norm squared here, I can simplify this whole expression to be the following. That what I've obtained is the following equality. That the L1 norm of w minus this sum of wi times the L2 norm of delta squared can be written as this plus this. So let me just write this. wi minus 1 over n times delta xi minus mu good plus sum I in s bad of wi delta x I minus mu of w. Okay, so this more or less fits on the screen, I guess. It's close enough. And let me bound these two terms again separately. So let me call this b sub good. We call this b sub bad. So let's start with b sub good. Let's actually introduce a little bit of notation first. Let me define delta I to be equal to 1 over n minus wi for all I in s and also in s removed. So these delta i's will have some nice properties. So in particular, the delta I is always non-negative for all I in this set, simply because for all I and S, we know that by our assumption, Wi is at most 1 over n. And for all I and S removed, Wi is 0. So then delta I is just equal to 1 over n. There's also another nice property, which is that the sum of the delta I for I in, S sub good. This is relatively small, at least if epsilon is pretty small, because I can write this as sum over I in S sub removed of delta I plus sum I in S sub good intersect S delta sub I. And this can be upper bounded because this is equal to sum over I in S sub R of 1 over n plus sum I in S sub good union or intersect S delta sub I. But this is at most epsilon n because the size of S sub R is at most epsilon times n. Or sorry, this is at most epsilon. And this can be upper bounded by just the sum over S of delta sub I, because the delta sub I are all non-negative. So I can just add in more non-negative summons. But this is equal to the L1 norm between W of S minus W, which is epsilon. So overall, the sum of the delta I is at most 2 epsilon, which means, I realize, there is a slight typo in this lemma statement, because I will require epsilon is less than or equal to 1/2, and I believe there will be a 2 epsilon here. But since we're always going to be considering epsilon which are very small, in particular less than 1/2, at least for now, this doesn't make a big difference. So this will also apply to the original theorem statement. I don't want to go back and append that. But anyways, neglecting that, the point is that if epsilon is less than or equal to 1/2, this implies that delta is in the subsimplex. Which will be useful in a second. So good, we have all these nice facts and for this delta I, and notice moreover, this is just equal to negative delta I. Okay, so now let's bound B sub good, and for some reason, let's bound B sub good squared. So what is B sub good squared? Well, I just rewrote it as sum over I sub good of minus delta I times delta inner product xi minus mu good, quantity squared. So let me just rewrite that here. I can throw away the minus because I'm squaring everything, so that doesn't matter. So this is sum over S sub good of delta sub I times delta inner product xi minus mu sub good, whole thing squared. And now what I'm going to do is I'm going to apply my Holder's inequality with AI being equal to delta inner product xi minus mu sub good, and bi is equal to 1. So notice I can do this because delta is a member of the subsimplex. And when I do so, what I get is that this can be upper bounded by the following. Sum over S sub good of delta I times delta inner product xi minus mu sub good squared times sum I in S sub good of delta I times 1 squared. Good, so we just argued that this is at most 2 times epsilon. And what we're going to do for this term is this slightly lossy looking inequality. What we're just going to say is that we know that delta I are non-negative, and the delta I are at most 1 over n. So I can just replace the delta i's with 1 over n's everywhere. And since these terms are also non-negative because they're squared, that will only be a valid upper bound on this quantity. So I'm just going to say that this is at most sum I in S sub good times 1 over n delta xi minus mu good squared times 2 epsilon. And the reason I'm going to do this is because now this has a very nice form, because this actually is equal to delta transpose the empirical covariance of the points in S good. So xi minus mu good outer product itself times 2 epsilon. And our original assumption, this star assumption, if you scroll all the way back, if you recall, to the very beginning, was that this has spectral norm at most C times identity. So it was upper bounded, by C times identity, which means that B sub good squared can be upper bounded by C times L2 norm of delta squared times 2 epsilon, which implies that the absolute value of B sub good is at most the square root of this quantity. So 2C epsilon times L2 norm of delta. Okay, good. So now we're going to try to do something very similar for B sub bad. So again, we're going to bound B sub bad squared. So if you recall, B sub bad squared can be written as the following: I in S sub bad of Wi times delta inner product X of I minus mu of W quantity squared. And again, what we're going to do is we're going to apply Holder's inequality, with AI being these and the BI being 1. So this is less than or equal to sum I in S bad of Wi times delta inner product Xi minus mu of W squared times sum I in S bad of Wi times 1 squared again. Okay, and again, the reason why we're going to do this is because the Wi for I in S bad is upper bounded, right? This is simply because the sum of the Wi in S bad is at most 1 over n times sum of S bad, which is less than or equal to epsilon n. Epsilon. And similarly to what we did before, what we're going to do to upper bound this quantity is we're going to apply what seems to be quite a loose upper bound. What we're going to simply do is replace the this sum, replace it from a sum over S bad to just a sum over everything, all the points in S. And again, we can do so because all the summons are non-negative. So we get this expression times epsilon. And the reason why we've done this is because now we actually have the quadratic form that we can control, because this is exactly delta transpose times the empirical covariance, or I should say sigma of W times delta times epsilon. Okay, and by the definition of the spectral norm, this is at most the spectral norm of sigma of W times the L2 norm of delta squared times epsilon. So this says that B sub bad squared, I should say, is at most this, which implies that the L1, or the absolute value of B sub bad, is at most the square root. It's the most epsilon times the spectral norm times L2 norm of delta. And now we're pretty much done, because if you remember, we had the following expression, which is that the sum of the Wi minus, the L1 norm, I guess, that's how I denoted it before, minus the sum of the Wi over S bad of delta L2 norm squared was at most B sub good plus B sub bad. And if you just substitute the bounds that we just obtained, so this bound and this bound, what you get is that the right hand side is at most square root of 2C epsilon times delta L2 norm plus square root epsilon times spectral norm of sigma of W times L2 norm of delta. And so these cancel with one of these terms. And now we're left with this, which is simply the L1 norm of W minus sum Wi for I in S bad times L2 norm of delta is at most 2C epsilon plus square root epsilon times the spectral norm of sigma of W. And now to conclude the proof, we just need to observe that the L1 norm of W is at least 1 minus epsilon, because we're within this set. You can only remove an epsilon amount of mass from the uniform distribution. And this is at most epsilon as well, because again, it's the amount of mass that W can place on the uniform distribution, or so over, it's upper bounded, excuse me, by the amount of mass that the uniform distribution can place on the bad points. So overall, this says that 1 minus 2 epsilon times the L2 norm of delta is at most this quantity. And if you just move the 1 minus 2 delta, or 2 epsilon to the other side, you get exactly the bound that we claimed. Cool, so that proves the lemma. Again, the original theorem statement, because I had these issues, have to be amended. The assumption must be that epsilon is at most 1/2, and the factor is 1 over 1 minus 2 epsilon, not 1 over 1 minus epsilon. But again, since we're usually going to be considering very small epsilon, this doesn't really matter. Okay, so that concludes the proof of this fact. Let me conclude the lecture by just actually relating this back to the original problem that we considered. Because recall, what we actually really care about is this problem, this statistical problem, where we have a distribution with mean mu and covariance upper bounded by the identity. And the goal is, given epsilon corrupted samples from this distribution D, learn the mean mu. So we want to apply the spectral signatures lemma we just proved to this problem. But unfortunately, it's not a priori clear what sets I can actually apply this to. Intuitively, if I have an epsilon corrupted set of points from a distribution, again, we always have this decomposition that S is equal to S sub good union S sub bad, set minus S sub r, where S sub good is a set of NIID points from the distribution. And you'd like to say I could just apply my lemma statement with this decomposition. The problem is that it's not actually clear if this decomposition is actually going to satisfy the assumptions of the lemma, because the empirical covariance actually of my set of points might not actually converge. So it might not actually be bounded in spectral norm. So it's a good exercise to actually try to cook up why this might happen. But we can always get around this because of the following sort of hack, which was first proven in a paper by Diakonikolas, Kamath, Kane, myself, Moitra, and Stewart, which said the following. It's a lot of math, but let me first just say what it says in words. What it says is that if I have a set of IID samples from a distribution with bounded second moment, it is true that the empirical covariance of the set of points might not be bounded, but I can always find a large subset of these points, which will have mean which is close to the true mean, and will also have bounded covariance. So formally, let epsilon be at most 1/2. If x1 through xn are just IID samples from D, then there exist universal constants such that with very high probability, there exists a set of points, S sub good, such that this is a large set of points, and the L2 norm between the true mean and the empirical mean of these set of points is upper bounded, and moreover, the empirical covariance of this set of points is also upper bounded in spectral norm. Okay, so there's some relatively complicated expressions on the right-hand side. We can just simplify this for sake of exposition with this corollary, which just says that if n is sufficiently large, then with very high probability, the empirical mean of this set of points is at most root epsilon away from the true mean, and the empirical covariance is upper bounded up to constants by 1. So now, if I have an epsilon corrupted set of points from a distribution D, here's how I can apply, or I can get into the setting of the lemma that I just proved. So in that case, I have a set S, which can be written as S sub good union S sub bad, set minus S sub r, where S sub good is NIID draws from my distribution D. So then, by assumption, or not by assumption, excuse me, by this corollary, we know that S sub good can further be written as, let's say, T sub good union T sub bad, where T sub good satisfies these things that are nice. So in particular, its empirical mean is close to the true mean, and it has large size and has bounded covariance. So let me just write that. Satisfies. So first of all, its size is pretty large. It's at least 1 minus epsilon times z. Secondly, the empirical mean of t sub good minus the true mean is upper bounded by up to constants, something like root epsilon. And thirdly, the empirical covariance of t sub g is bounded in spectral norm. It's at most up to some constants 1. So then what I'm going to do is I'm just going to pretend that instead of having n IIDs, like an epsilon corrupted set of samples from D, I'm just going to pretend that my good set of points were really just t sub g to begin with. Because I know that if I can learn the mean of t sub g, then by equation 2 or by fact 2, I can also learn the original mean up to some root epsilon factors, which I can't help but lose anyways. And notice that t sub g is in this setting that I care about. So in other words, I can write S as equal to t sub good union t sub bad union S sub bad set minus S sub removed. And I can just define a slightly bigger set of corruptions, which includes both t sub bad and S sub bad. So I lose a little bit in epsilon. I think I double epsilon. But now I do have a set of points t sub g to which I can apply my lemma. So now in particular, if I can learn the empirical mean of t sub g, I can learn the empirical mean, or sorry, the true mean of S, and moreover, one way to certify if the empirical mean of my current set of points is a good estimate of the true mean of t sub good is just to take the empirical covariance and take its top eigenvalue. Okay, so that's pretty much it for this lecture. The plan for the next lecture, I believe, will actually be, next lecture will be a bit short, I believe. It will just be to prove essentially this lemma that I'm showing on the screen right now in a slightly self-contained way, more or less self-contained. And then the lecture after that, we will actually use the main lemma we proved today, this spectral signature stuff, to actually derive a relatively straightforward algorithm that is polytime and gets root epsilon error for robust mean estimation under bounded second moments. So that's it.